Okay, so welcome back. So at this point, we have the basic definitions of set theory. So we know what subsets are, we know what proper subsets are, we know what element means, we know how to represent a set, and we know some basic Venn diagrams. And we're going to go forward with these concepts. But first, I want to give you some more complicated sets that you might see in practice. So it's important to note that sets can be objects in other sets. So we can have a set inside of a set if we wanted to. And I'm going to show you an application of that in 1 second. But for now, let me show you what that looks like. I can have a set A, which is the set, let's call it 1, 2, 3. Okay. And then I can have another set, we'll call it U, which is the set 1, 2, 3. But it also has another set 1, 2, 3. And let's say another set 4, 5. Okay. Now, it's important to note the opening and the closing of these brackets because we can theoretically imagine what these sets are, what they theoretically look like. Because A looks like a box with 1, 2, 3 in there, right? U looks like a box with 1, 2, 3 in there, but also another box with 1, 2, 3 in there, and then another box with 4 and 5 in there. So I hope you can see this because the opening and closing brackets will indicate the beginning and the end of a set. So if we were to ask, what is the size of A? So what is the cardinality of A? In this case, it's 3. We have 3 distinct objects in this set. Whereas if we ask, what is the size of U? The size of U is 5. Okay, so please note this. We have 1 object, 2 objects, 3 objects, and then another box and another box. That makes 5 altogether. So now we can use the symbols that we talked about before again, and we can see how it pertains to these types of sets. So for example, if I have A is a subset of U, okay, is this a true statement? Is it true that A is a subset of U? Now, A is a subset of U means every element in A is also in U. Every element in A is also in U. So is that true? Well, the elements in A are 1, 2, and 3. Are they individually in U? The answer is yes. So this is a true statement. Okay, so A is a subset of U. All right, another question. Is A an element of U? Now, just before we get into this answer, the reason for A is a subset of U is that 1 is found in U, right? So 1 is in U, 2 is in U, and 3 is in U. That is the reason behind this being true. All right, the second question is A an element of U? Okay, so is A an element of U? Well, once again, the answer is true. The answer is yes, because not because of those first 3 items, but because of the fourth item here, right? Because this object, this set is an object that is found in U. Okay, so the reason for this is that the object 1, 2, 3, right? This object 1, 2, 3 is an element of U. Okay, that is the reason why the second statement is true. Now, another way to say that is if this statement, if this set was not there, then this would be a false statement. Okay, so just take note of that. So A is a subset of U. A is also an element of U. Now, the next step that I want to take is the set containing A. The set containing A. Is this a subset of U? Now, I want you to be careful here. In fact, on the side, I want to write down what the set containing A actually means. So the set containing A looks something like this. Now, don't let the double squiggly line confuse you there. It really means that this set has one element. Okay, this set has one element. This is the element. Okay, this set has one element. So can I say that the set containing A is an element of U? Is every set on the left-hand side in U? Sorry, is every element on the left-hand side in U? The answer is yes, because, well, the only thing that's here is that A is in U. Okay, now, in fact, I think I should leave that here, which is going to help in the next example. But I want you to take a quick look at the last 2 examples. Okay, the last 2 questions turns out to be the same question, right? Saying is A an element of U and saying the set containing A is a subset of U is really saying exactly the same thing. Okay, they're both true for the same reason. So I just want you to see that. Okay, last question. Can I say that the set containing A is an element of U? Now, an element means that this exact object must be found in U. Okay, so this exact object must be found in U. And in this case, we can say that this is false. Okay, it's not true because this element, right, the set containing A is not one of the elements that's found in U. Now, you might say, what about the fourth object? Doesn't that look like this? Well, no, because this object has two squiggly lines, right? So it's a box inside of a box. So for it to qualify, it must match exactly. Okay, so I hope that makes sense. So another way to say this is if I imagine that there is a object that looks like this, right? So if you take a look at the set A and there is a double squiggly bracket around that 1, 2, 3, then yes, this would be true. But as is, it is not a true statement. Okay, so I hope you start to understand how the subset and the element notations work with sets inside of a set. Okay, so this is going to become an issue moving on. So I just want you to see that as an example. I'll label this 5-8 if you're following along. All right, now in the last video, we talked about some ways that we can do, we can define subset and proper subset. So I want to use some of those definitions in a proof here. So we're going to do two proofs, theorem 1 and theorem 2. And both of these proofs are actually pretty similar. And they work upon the definitions that we were given for subset and proper subset. So let's take a look at some of these. So the first one is that if let A, B, and C be sets in a given universe. So let's take a look at the first statement here. If A is a subset of B and B is a subset of C, then A is a subset of C. Okay, now we want to prove this. And just for a second, maybe intuitively, we can think whether or not this is true. So if everything in set A is also in set B, and everything in set B is also in set C, then surely everything in set A is in set C. Right? So intuitively, I hope that makes sense to you. But let's try to write this out. Now, what I'm going to write out here is what's called an element argument. Okay, so this is called an element argument. And what an element argument is I'm going to write the definition of the premises as well as the conclusion, and I want to show that this is a valid statement. Okay, I want to write out the definitions of the premises and the conclusion. I want to show that this is a valid statement. Now, once I do that, you're going to see right away, oh yeah, this is a valid statement. So if I say A is a subset of B, then that means for all X, if X is in A, then X is in B, right? That's that part. For all B, sorry, for all elements, if X is in B, then X is in C. So therefore, I want to say for all X, if X is in A, then X is in C. And that is A is a subset of C. So that's the conclusion we want to make. Can you see that this is a valid argument? Now, in fact, we did an example just like this, right? So if you can look back on the videos that we did for first order logic proofs, right? The proofs video, we actually said that this is syllogism, but not exactly. We needed to do a generalization, then we needed to apply the syllogism, then we needed to do a generalization. So I hope you still remember that example. If you don't, please go back and review that. But this is a form that is valid. So I'm not going to do that proof again. So I'm just going to say that this is a valid form, and this was proven in the first order logic. Okay, so it was proven in first order logic already. So I'm not going to do it again. Now, that's not very interesting. The second one, the second statement, is a little bit more interesting. So the second statement not only has subsets, but it incorporates proper subsets as well. So if I said A is a proper subset of B, now the conclusion that I can make is that A must be a proper subset of C as well. Okay. Now I want you to think back. What is the definition of a proper subset? So the definition of proper subset is that everything in A is also in B, and there's an extra object in B that's not in A. Okay, so this is something extra that we have to add to our proof. All right, so let's try to incorporate some of this. So I'm going to prove the second part. So I'm just going to use this double star. So I want to prove the double star. Okay, I'm going to say that everything above is still applies. Okay, so everything above still applies. Okay, so we have the fact that we have, the two premises are true, and we also have the conclusion that we've proved already. Okay, so everything above still applies. But in addition, what can we add to it? Well, since A is a proper subset of B, we can also add that there exists an X that is in B and is not in A. Okay, now again, let's just take a step back. I'm going to go back a couple slides when we first introduced this idea. We said for a proper subset, number one still applies. Yes, that still does apply, but there's an extra element in B that is not in A. So we've just added this to the proof. Okay. Now, since there is an element in B and not in A, do you agree that this means that there is an element in B and not in A? So I'm just copying this down. And this same element must be in C as well. Now, what did I just do? I added this X is in C, but why can I say this? Well, because we have a second statement here that everything in B must be in C. Right? Everything in C must be in C. So since X is in B, immediately I can add this there because B is a subset of C. Okay, so again, make sure you understand this point, but ultimately, I can now claim that there is an object in C and not in A. Okay, and I'm just going to label this. I'm going to label this number one, and I'm going to label this number two. Okay, and now I'm going to claim because number one and number two are true, right? So for all X, X in A implies X is in C, and there's an extra object in C that's not in A. Therefore, I can say because of this, I can now say A is a proper subset of C. And that's it. That is my proof for double star. Okay, so I hope you can see how this plays a role, how these quantified definitions play a role in solving these theorems. Now, what I want you to do is in your own time, please take a look at the second and third statements. So take a look at these statements and make sure that you're happy with them. Make sure you can prove them. The proofs are actually very similar to what we've done here. So again, try them. If you have any questions, please come to the office hours. Please send me an email and we can discuss them. All right. So let's take a look at theorem 2 now. So theorem 1, I hope everyone's okay with that. Let's take a look at theorem 2. Now, theorem 2 says, let A be a set in a given universe U. Okay, so A is just some set. Then the empty set must be a subset of A. So another way to say this is that the empty set is a subset of anything. Empty set is a subset of anything. Okay, so this is the first part. And then also means and. So there's actually a second statement here. If A is not the empty set, then that means it is going to be a proper subset of A. The empty set is going to be a proper subset of A. Okay, now again, let's see if we can use the definitions that we know in order to prove this. Now, for the proof that A sorry, empty set is always a subset of A. And it doesn't matter what A is. Okay, I'm going to use a proof by contradiction. Okay, so by contradiction, I'm going to assume that empty set is not a subset of A. Now, again, I want you to recall, what is a proof by contradiction? The first thing we do is assume the opposite. Okay, how do we assume the opposite here? Well, I assume that the empty set is not a subset of A. And what do we have to show? We have to show this is impossible. Okay, now, luckily, we have this definition for not subset. So again, I'm just going to go back and we defined not subset. So what does it mean that A is not a subset of B? There is an element in the first set and not in the second set. Okay, there is an element in the first set and not in the second set. So there is an element in the first set and not in the second set. All right, so what do you see? There is an element in the empty. Right away, I can stop you there, right? Because by definition, there's nothing in the empty. So this must be a false statement. If this is a false statement, what did we just show? We showed that empty set must be a subset of anything, right? So empty set must be a subset of anything. And that's true. That is a true statement. Okay, so moving on, we want to show that if A is not empty, so in addition to this, if A itself is not the empty set, so let's take a look at the second part of this. So I want to show if A is not the empty set, then I want to show that empty set is a proper subset of A. And again, I'm going to use the same technique that we did in the previous slide, previous proof. I'm going to say everything above still applies. Okay, so everything above applies. But in addition, I want to add this. If A is not the empty set, then that means there is an element in A. Right? So we've assumed that A is not the empty set. So there must be an element, at least one element in A. Now, this same element, whatever this element is, cannot be in the empty set. So this is by definition. Right? So by definition, this thing cannot be in the empty set. So what did we just show? There is an object in A that is not in the empty. So what can we say about this? Because of, we're just going to show that number one is true. Number two is also true. So because number one and number two are true, therefore, we can claim that empty set must be a proper subset of A. Okay. So ultimately, in the last two proofs, what we did was we used the definition of the subset in order to prove, or proper subset as well, in order to prove this statement. Okay, so just remember what techniques we used. Anytime you want to prove proper subset, you have to prove that everything in the first set is also in the second set, and there's an extra item in the second set that's not in the first set. So just keep that in mind. Okay, so the next thing we want to talk about is an application that is actually pretty useful in a lot of problems that are solved in computer science. So given a set A in some universe, we call a power set of A, and it's denoted by capital P, although it's actually sometimes a fancy P. Okay, so in some textbooks, you'll see it written as like kind of a, how do you draw a fancy P? Kind of like that. Okay, so it's kind of like a fancy P of A, and this denotes the power set of A. And what the power set of A means, it is the set of all subsets of A. Okay, it's the set of all subsets of A. All right, so that means you're going to find a set within a set within a set. Okay, so let me give you a quick example of this. So if we had a set A, and the set A is 1, 2, 3, okay, and I want to find out what the power set of A is. Now, again, the definition of the power set of A is the set of all subsets. Okay, so let's figure out what are all the subsets of A here. Well, one subset is this one, right? So this is a subset of A. Okay, convince yourself of that. This is a subset of A. This is a subset of A. 1, 2, also a subset of A. 2, 3, also a subset of A. And finally, 1, 2, 3 is also a subset of A. Now I am missing one. If you remember in the previous example, we said empty set is a subset of anything. So one thing you can gather is whenever we do a power set, whenever we write a power set, the empty set is always going to be there. Okay, so just right away, you can write down empty set first and then everything else. Okay, so I just wanted to leave that as a point. So as we said, it is the set of all subsets. Okay, so it is a set of all subsets. Now, if you count here, how many subsets are there? Okay, so how many subsets are there? There's 1, 2, 3, 4, 5, 6, and 7. So that means I'm actually missing one. I'm missing 1, 3. There we go. There should be 8 subsets of A. Okay, so I have 1, 3 there in the middle. Now, the question here is we want to find the size of P of A. Okay, so the size of P of A here is equal to 8. The question is, where does this 8 come from? Now, I want you to note that these subsets don't have order. So for example, if I say 1, 2 is a subset of A, then I've already really included the set 2, 1 in that. Okay, so the order of the subsets don't really matter. So there's really only 8 unique sets that are subsets of A. Now, where does the 8 come from? Well, it's actually a counting problem. Because if we want to know whether or not each of these objects belong in a subset, so I'm looking at the number 1, 2, and 3, and I'm basically answering the question, do I include it or do I not include it into the subset? So I'm basically saying yes or no to the number 1. I'm saying yes or no to the number 2, and I'm saying yes or no to the number 3. Right? So it's yes or no, yes or no, yes or no. And if you want to apply this to a counting problem, you have 2 choices for each one of those objects. So the answer is 2 times 2 times through 2. This 8 is really from 2 to the 3. So generally, if we say that, so in general, if the size of A is equal to n, then the size of P of A is 2 to the power of n. Okay, or another way to say that, it is 2 to the size of A. Okay, so just remember this as a definition. This is actually an important theorem that we're going to come back and use later on in the course. But we can actually see where this equation comes from. So let me ask you another question, which is pertaining to subsets. So if I want to find out the number of subsets, of A of size K, what is it? Okay, now let me do the example that we had before. So if you take a look at this example P of A, I have the subset 1, the subset 2, the subset 3, and so on. If I want the number of subsets of A of size 1, then how many are there? Well, the answer here is there's 1, 2, and 3. Right? All of those have size 1. So the answer is 3. How many subsets have size 2? The answer is 1, 2, 3. 3. 3 subsets have size 2. How many subsets have size 3? Well, the answer here is 1. How many subsets have size 0? The answer is 1. So where do these numbers come from? Well, essentially what we are doing is from the set A, we are choosing certain number of objects. Right? From the set A, we are choosing a certain number of objects. So what did we say? Every time we use this word choose, we are talking about a combination. Remember now, the numbers, the elements themselves, the order does not matter. The only thing is it's in the set. Right? So I want you to see that when I say how many subsets have size 1, the answer was 3 choose 1. Right? So from 3 elements, choose 1 element. How many subsets have size 2? From 3 elements, choose 2 elements. How many subsets have size 3? From 3 elements, choose 3 elements. I hope everyone gets the idea, right? So from the total number, I'm going to choose the size of the subset. So the number of subsets of size A that have size K, what's the answer? Well, N, choose K. Okay, the number of subsets of A of size K is N, choose K. All right, so how does this help us? How does this equation help us? Well, remember before we said that if I wanted to have the total number of subsets, right? So the P of A, the power set of A, I can say that N choose 0. So how many subsets have size 0? How many subsets have size 1? How many subsets have size 2? All the way up to how many subsets have size n? So if I take the sum of all of these, and these are independent statements, by the way, they are mutually exclusive from each other. So I can just add them independently, and I should be able to get the final solution. And by the way, what is the final solution? The total number of subsets that we have in this case is 2 to the n. Do you remember this equation? If you don't, take a look back in topic 1. So in topic 1, when we did the binomial theorem, we said one application of the binomial theorem says n choose 0 plus n choose 1 plus n choose 2 all the way up to n choose n is equal to 2 to the n. So if you don't remember that, please go back and take a look at that. And that's where this equation comes from. So this is just another way to show that that equation is actually true. Okay, and this is being applied onto power sets, or the number of subsets altogether. Okay, so the last thing I want to discuss here is a quick application on Cartesian products. So Cartesian products, we're going to actually look at the application of Cartesian products. But for now, I just want to show you what they are. So for example, if I have a set like A is equal to 1, 2, and B is the set 3, 4, 5, then I can define a cross product on these two sets. I can define A cross B, right, as a bunch of what we call tuples. Now here you see two sets. So that means the tuples that we're going to define are in this form, are in the form of an element followed by another element. And basically we want all the crossings where the first element comes from A and the second element comes from B. So one example would be 1, 3. Another one would be 1, 4 and 1, 5. We also have 2, 3, 2, 4, and 2, 5. So again, the first element comes from A, the second element comes from B. So this is A cross B. Now, of course, the order here does matter. So A cross B is not the same as B cross A, because B cross A would mean that the first element comes from B, the second element comes from A. So here we would have 3, 1, 3, 2, 4, 1, 4, 2, 5, 1, and 5, 2. Okay, now notice, unlike sets, the tuples, these round brackets do have order. Okay, so saying that we have a tuple 1, 3 is different than saying that we have a tuple 3, 1. Okay, so those are different things. Now, in addition to this, we probably won't look at this application in this course, but we could have multiple sets. We could also have a set C, for example, that is 6, 7, right? And we can define a set A cross B cross C, where we would have tuples that are all 3. So the only difference here is that we have the tuples, all of the different combinations where the first element comes from A, the second element comes from B, and the third element comes from C. So we would have something like 1, 3, 6, 1, 3, 7, 1, 4, 6, 1, 4, 7, and so on, right? So we would have all of these different combinations, and all of them are going to be in the set A cross B cross C. All right. So when we come back, I'm going to pause the video here, but when we come back, I'm going to do an application of what we've just talked about. I'm actually going to skip over this XY plane problem because we actually skipped over it in counting as well. There is this problem in the textbook. So I invite you to take a look at that. But the theorem, this theorem is actually a pretty famous theorem from Pascal. So I want to take a look at that theorem. And I'm going to take a look at a few applications that come from this theorem. It turns out that it's a very nice application from set theory. So I want to take a look at that after in the next video. Okay, so right now I'm going to stop this video and then we're going to continue on in the next video.